Greetings, ladies and gents, and welcome back at Mike Maths and Science Club. In this video, we'll be looking at vertical projectile motion graphs. Now, before I proceed, I just want to say that if you have any topic that you're struggling with or that you would like me to cover next, I welcome all suggestions, ladies and gents. You're more than welcome to just throw the name of the topic in the comment section, right? Now, when it comes to a vertical projectile motion, we have three types of graphs. So we have what is known as the velocity versus time graph, which is what we'll be covering in this video. We also have the position versus time graph and the acceleration versus time graph, which the rest will cover in the in the videos to come. Right now, in any graph, as you know, we have in this case the x-axis, right, and in this case the y-axis. So in this case, in any graph, in this case we know we have in this case the y-axis. Now that's terrible, right? We have the y-axis in this case, and also in this case the x-axis. All right, now when it comes to the velocity versus time graph, we actually have in this case we actually have the y-axis representing the velocity, and in this case the x-axis representing time. So in this case we have in this case the y-axis representing in this case the velocity, right? And we have in this case, so in this case we know that of course velocity is measured in meters per second, right? And we say that we have in this case time being represented by in this case the x-axis. So in this case we actually have time there, change in time in this case measured in seconds. Now please note in this case that in this case velocity is a vector quantity, meaning that of course it can also have in this case it can also be negative. So in this case that would be where we would actually have our zero there. So in this case we would know that of course going up would be positive, and in this case going down in this case that direction it would be in this case it would be negative, right? So in this case that's one thing that you must keep in mind. So in this case when it comes to the velocity versus time graph, in this case our velocity there, or y, can also be in this case negative, right? And in this case what you need to note also is that in this case we said of course the x-axis represents time. Now unfortunately we do not have negative time. We don't have that happening unfortunately, because in this case we know that time is a scalar quantity. It can only be positive. We do not have in this case negative time. So you must just keep that in mind. In this case the y-axis represents the velocity, and the x-axis represents in this case the time, or the change in time. Now my approach on this section will be a little bit different, as I will be introducing this graph using scenarios. Right now, scenario one, let's just let's just run through this scenario so that we don't make this video the longest video alive, right? So scenario one, let's say scenario one there. Now suppose I was standing on the ground, right? Now suppose let's say that same like there, all right, and I project a steel ball up. So in this case, let's say suppose I project it up with a velocity of 12 meters per second. So in this case what would happen is that, so in this case we know that in this case the velocity there would simply be in this case 12. All right, so in this case what I'm going to do would be to take upwards as positive and downwards in this case as negative. So that would mean that the velocity at that point would simply be in this case 12 meters per second. I'm just going to put that as numbers, right? In this case that velocity there. So in this case what would happen is that this object will go up, all right, it will reach a maximum point, and in this case what would happen is that it would now begin to fall down, all right, in this case passing that point. In this case, now suppose let's say I projected this object upwards in this case from a certain height, let's say h, right, above the ground. Let's say that's point A, that's height h there. So in this case what would happen is that of course it will reach that point of throw there, where it of course it returns to the same position, but in this case on its way down. So in this case I'm going to treat this point as point A, that's point B, so it's simply be in this case point C. So in this case what will happen is that if I miss this object, so in this case what will happen is that it will continue to travel downwards until in this case it reaches the ground. Right, so in this case until it reaches the ground there. Right, let me just, yeah, right. So in this case until it reaches the ground. Then now suppose, let's say it reached the ground, we in this case after time, in this case 5.3, right? And then let's say with a velocity of negative 20, of negative let's say negative 20, right? So that would be the velocity. So that simply be in this case point D, right? So the velocity we know that would be, so in this case we know that v point D would simply be in this case a negative 20. Now remember that in this case we know that of course the velocity, we actually know the velocity is at point C. So in this case we say that these 2 points in this case they have the same speed, but in this case the only difference would be the direction of that speed. We discussed that in the previous video. Now I'm not going to go through much of what we discussed. Reason for that, I'm sure you already know. I don't want to make this video the longest video alive, right? So in this case, if this doesn't make sense, in this case of course in terms of the fact that of course the speed, these 2 points in this case is equal, you can the speed of the object on these 2 points are equal, you can just refer to the previous videos. Right, now in this case we would know that of course the speed of at point C would simply also be it would be negative 12, right, in this case. Now according to what I said here, we say that of course now let me just put more information. Right, now let's say suppose this object, let's say took 2 seconds to travel between point A and B. So that would mean that of course it took the same amount of time to travel between point B and C. So that would mean that if between point A and B is 2 seconds, so that would mean that between point C or between point B and C, it would take the same amount of time, which is in this case just 2 seconds. So we would know that of course it reached at point B at point C, in this case after 4 seconds. So in this case this would be 2 plus that 2, so in this case that point would simply be in this case 4 seconds. So in this case we would know now if I were to, so in this case we say that's 2 seconds, and that's 2 seconds there as well. So in this case if I were to treat these 2 points now remember according to what I said there, we said in this case we are going to represent in this case the y-axis is in this case the velocity, and in this case the x-axis is in this case the change in time or time, right? So that would mean that anywhere at any given point, so that would mean that in this case x would simply represent time, and in this case y would simply represent in this case it will simply represent the velocity, right, of the object. So that would mean that at point A we actually have, in this case we know that at point A time would be 0 there, so in this case we actually have time being 0. So if I were to treat this as coordinates, so that would mean that in this case my x is 0, so in this case my y would simply be in this case 12. Right, now when I get at point B, so that would mean that we know that of course the velocity at point B, at the maximum point, we know that the velocity there is 0. So in this case we say that it took 2 seconds to travel between point A and B. So that would mean that in this case y at point B would simply be 2. All right, so the y would simply be 2. Just write that down. There's simply be 2, and in this case our x, in this case our y, would simply be in this case 0. We know that of course the velocity at the maximum point would simply be, in this case it would simply be 0. So in this case that 2 there would simply represent x, then in this case that 0 there would simply represent y there. So in this case when we get at point C, so that would mean that in this case our y would simply be in this case 4, and in this case our x would simply be in this case negative 12. So that would mean that when we reach at point D, according to what I wrote there, so in this case that would mean that in this case our y would simply 5.3, and in this case our x is simply in this case a negative, in this case our y is simply a negative 20. Right, now if I were to plot these points in a graph or on a graph, so in this case I want you to note the type of graph that I'm actually going to produce. Right, let me just adjust this, right, so that it fits there nicely. Right, don't want to make this it's big. So in this case we know that of course this will be in this case our x, and that will simply be in this case our y there. So if I were to plot these points, so in this case that would simply mean that in this case at this point here, we know that would be in this case 0 is to 12, and we know that of course that point would simply be there. So in this case, we said it's the y-axis represents the velocity, and the x-axis we said that it represents, in this case, the change in time. So in this case, that would simply mean that in this case, point A would simply be there, where it's, in this case, we have 0 is to 12, and in this case, point B, which is 2 is to 0. So in this case, suppose let's say that's 1, 2, 3, 4, 5, 6 there. So this simply, so in this case, that point B would simply be at that point there, right? And then of course point C, simply just going to plot these 2 points, right? So in this case, that would mean that in this case, point C, in this case, is 4 is to negative 12. So in this case, we have time being, in this case, no, that's not right. So in this case, that's 6 there, right? So in this case, not 0, that's 6 there. So in this case, we would actually have that point there, which is point B. In this case, point C would simply be at 4 is to negative 12, which would simply be around, I think, there, right? In this case, point D would simply be, in this case, 5.3, which is somewhere there. I think if I plot that point, would simply be somewhere, I think somewhere there. I think that's about right. So in this case, if I were to join these 2 points, now I want you to note the type of graph that I'm actually going to produce there. So if I were to join these points, right, starting from that point there, right, I hope that's gonna come out correctly. So in this case, what you would note is that what I formed there is simply a straight line graph, where in this case, this is the starting point, right? And then in this case, this is the maximum when where it returns on the same point. And this is when, of course, it reaches the ground. Now the question is this always going to be the case? And the answer to that is yes. The velocity versus time graph always forms a straight line graph. Now note the starting point. In this case, now note that the starting point, this will simply be, in this case, point A. And I'm just going to label those points. So in this case, simply be point A, that's point B, that's point C, that will simply be, in this case, point D. So in this case, when your graph cuts the y-axis, so in this case, this will be where, in this case, your object is at its initial position. So that's one thing that you must keep in mind. Right? So in this case, when your graph cuts, in this case, the y-axis, so in this case, this is of course when your graph is at its initial position. So you must just keep that in mind. And in this case, when your graph cuts, in this case, the x-axis, please listen carefully to this one. When in this case your graph cuts the x-axis, so in this case at that point B, so in this case, this is where, in this case, your graph is, in this case, this is where your object is at its maximum points. In this case, point B would simply be, in this case, at the maximum point. So in this case, when your graph, in this case, cuts the x-axis, so in this case, this is where, in this case, your object is at its maximum point. So you must just keep that in mind. So in this case, point C would simply be where, when it returns to the same position, of course, where it started. And then in this case, point D would represent, in this case, the where in this case the object, in this case, before actually it reached before it became in this case, or before it collided in this case with the ground. So in this case, that would simply be point D there. So in this case, what you need to note is that in this case, when your graph cuts the x-axis, so in this case, this is where, in this case, your object is at its maximum point. Now note that in this case, on this example that I took there, I took upwards as positive. Now if I had taken downwards as positive, this would have been the type of graph that I would have, in this case, produced. So in this case, if I had taken downwards as positive, so that would have meant that in this case, my initial velocity would have been negative 12. So in this case, my graph was going to be something, so in this case, it would have started at negative 12. This case reaches the maximum point, and then in this case, it will now start to travel in the opposite direction until it, in this case, passes this, the point of throw, where in this case the speed would be the same, but in this case the direction of that speed would be, in this case, different. In this case, it will continue to go down until, in this case, it reaches that the ground. Right? So that would be that point there. So that simply be point D. That would simply be point C there, and that would be point B, and that would simply be, in this case, point A. So in this case, if we had taken in this case downwards as positive, our graph would have just reflected upon that line x-axis. So in this case, y coordinate simply just changes the sign. Right now, when it comes to the velocity versus time graph, there are two important facts that you need to know. All right, and the first fact about this graph in this case is that the gradient underneath the velocity versus time graph actually represents the acceleration of the object, which in this topic we said that it actually represents the acceleration due to gravity. So in this case, what you need to note is that the gradient in this case underneath this graph actually represents in this case the acceleration of the object, which is actually always this case 9.8, but in this case, depending in this case on the direction that you took as positive, so of course it can also be in this case negative. So that would mean that according to that graph, in this case the first one, so in this case we're going to have in this case our gradient being equals, we know that of course gradient is calculated by saying in this case the change in y divided by the change in x. So in this case it will simply be in this case the change in velocity divided by the change in time according to what we have there. So in this case, so this is always the case. So in this case, this is when we took in this case upwards in this case as positive. So in this case, that's so in this case we actually have in this case the acceleration being positive, being negative rather. So in this case simply be in this case negative 9.8 being equals to in this case v final minus v initial equals to in this case t final minus in this case t initial. So you can also use that equation there if you're trying to find either the velocity or in this case a time, right, when you have of course the rest. So you can also use that. And in this case, according to this graph, if we had taken, let's say upwards, let's say downwards, rather downwards is positive. So in this case would say that in this case, so let me just take another color there. So in this case, say the gradient is equals to in this case the change velocity divided by the change in time. So in this case, it will simply be in this case positive 9.8 equals to in this case v final minus v initial divided by in this case t final minus in this case t initial. So in this case, what you need to note is that the velocity, in this case the gradient underneath the velocity versus time graph represents the acceleration of the object, which is always 9.8 meters per second, but in this case depending on the direction that we take, in this case as positive. So if we take upwards as positive, so in this case that would mean that the gradient is negative, so it would be a decreasing graph, right, like that one. So in this case, if we take downwards as positive, we would actually have an increasing graph, so that would mean that the gradient there would be in this case positive. And the second important fact about this graph, or about the acceleration versus time graph, is that the area underneath the velocity versus time graph actually represents the displacement of the object. So that's one another important fact that you need to note. So in this case, the area underneath the velocity versus time graph actually represents the displacement of the object. So in this case, if you're trying to find the displacement, now if let's say I were to to drop a perpendicular height, let's say between point B and C. Now suppose let's say I was trying to find in this case the velocity, in this case the displacement between point between point B and C. So in this case, what I would do in this case would be to drop in this case to drop the perpendicular height. So in this case, what I would have formed there would be a right angle triangle. So in this case, what you simply do in this case, so in this case you would notice that in this case this would simply be in this case the perpendicular height, and that would simply be in this case the base. So in this case simply be in this case the base. So in this case, what you need to note in this case, now you notice that this is actually a right angle triangle. So in this case, we know that of course to calculate this case the area of a right angle triangle, we say that a half multiplied by the base multiplied by in this case by the perpendicular height. So in this case, we know that of course the base would represent in this case the time. So this case would be a half multiplied by the change in time multiplied by the change in so in this case the perpendicular height, we say that's velocity, so in this case it will be multiplied by the change in velocity, right? So in this case it simply be in this case a half multiplied by t final minus in this case t initial multiplied by in this case by v final minus in this case v initial. So that's what you would simply do there. So in this case, if you are trying to find in this case, let's say that height there between point A and let's say between point A and D. Now what you cannot do is to calculate that directly between point A and D without using the equations of motion. So if they say that calculate the displacement between in this case, or calculate the height of the object or height h. So in this case, we would know that of course what we can simply just do there would be to calculate the displacement between these 2 points, right? But if they say without using the calculator, so in this case what you simply need to do would be to choose between point C and D, because that simply gives you again the height of the building, right? It will give you the same displacement. So in this case, so what you simply do there would simply be to say between point C and D according to this graph that we have there. So in this case, simply have, so between point B, between point C and D. So in this case, simply be that point there. So what you simply do there would simply be to create your right angle triangle. So in this case, simply do that there. So in this case, what you would form there would be in this case a right angle triangle, where in this case this length there is represented by the difference between these 2 points. Here. So in this case, if you look at what we have there, so in this case simply be in this case your velocity. So in this case, what simply do would be to say a v final. So you say 20. This case, so in this case, you simply have to substitute also with the direction, right, of that of the velocity. So in this case, what you simply do there. So in this case, if we start with time, so in this case, this distance that you have there would be in this case your height there. So in this case, this distance that you, in this case the base, would simply be represented by the difference between this case these 2 points there. So in this case, what you simply do there would be to say, so you'd say half multiplied by t final. So in this case, t final between these 2 points, there. So say in this case 5.3 minus 4. So in this case would be 5.3 minus in this case 4. In this case multiplied by v final. In this case this would be 20 there. So this case would be 20 minus, in this case, now this minus is simply just the part of the formula. So in this case simply be minus, in this case that minus 12 there. So we have 12 there, so simply be in this case minus 12. And in this case, you just put that into your calculator to simplify whatever displacement that is. So in this case, you'd actually get the negative answer there, which is normal, because in this case, that's the displacement. So in this case, these are the important things that you need to know, because sometimes they say calculate the displacement or calculate the height of the building, but in this case, without using the equations of the motion. So in this case, what you simply need to know, to remember, is that the area underneath the velocity versus time graph actually represents, in this case, the displacement of the object. So in this case, you must keep this in mind, right? So in this case, when we get to the examples that we'll do next. All right, now scenario number 2. Right now, this was a steel ball. Now we know that of course a steel ball doesn't bounce. So in this case, for scenario number 2, let's just go to scenario number 2 there. Scenario 2. Now suppose, let's say I was dealing with a tennis ball. Right now, suppose let's say I was standing there again. That's same mic. Then I project, in this case, I project the tennis ball upwards. At least projected upwards. Now I'm not going to put values. So in this case, suppose let's say I was dealing with a tennis ball, like I said, and I projected upwards. So in this case, what would happen is that it will do the same thing as in scenario 1. So in this case, it will go up to reach a maximum point. In this case, it will in this case travel down to pass that same point there. In this case, no, that doesn't look good. So in this case, it will pass that same point there. So it simply be point A, point B, point C. So in this case, what will happen is that it will continue to go down until it reaches the ground. So in this case, what will happen is that it will, in this case, this object will collide in this case with the ground. In this case, what would happen is that it would go up, it will reach a maximum point, right, a certain maximum point, and then in this case it also starts to go down again. In this case it will reach it will collide with the ground again. It will go up until it reaches again another, in this case another maximum point there. Now what you need to note, and of course according to what we say, according to what we said in this case in the previous lesson, right, now when it comes in this case to a bouncing ball, the only difference that comes when it comes to the graph is that in this case your graph will now have in this case it now have multiple in this case maximum points. In this case that will simply be due to the bouncing of the object. So that's the only difference that is there. So in this case the type of graph that you're going to have is simply the same type of graph, simply be the set line graph, but in this case this graph in this case would simply have multiple maximum points, in this case due to the bouncing of the object. So in this case now, like I said, so in this case simply be in this case point A, that's point B, that's point C. Now what you must keep in mind is that now when we in this case talk about the velocity of the object, in this case the final velocity of the object on the ground, we simply talk about the velocity of the object before it comes in contact with the ground, right? So in this case I'm going to represent that point being point, so that's point A, B, so that's going to be point D there, right before it collides with that with the ground. So in this case after it collides with the ground, so in this case what you must notice that immediately after in this case it collides with the ground, so in this case it will go up. So I'm going to in this case to represent that that point being in this case point, so that's point D, so that's going to be point E, and then in this case this maximum point I'm going to present it F. So in this case it do the same thing. I'm going to look at the velocity of the object before it in this case it collides with the ground, just split seconds before it collides with the ground. So in this case it will be in this case point EF, so this would be point G, and in this case after this would be point H, and that will simply be in this case a point I. Now with the tennis ball, in this case what would happen is that this tennis ball will bounce. In this case it will reach the ground with a certain speed, and it will collide with the ground. Now after the collision, right, its speed will change direction, and all of a sudden it will become positive. So let me just draw a graph of this of what is happening there. So in this case, if let's say I were to draw, now remember we said we're going to produce the same type of graph, but in this case with multiple maximum points. So in this case what I'm going to do would be to just draw another in this case a graph. So in this case what's going to happen now is that, now remember that it started with a certain in this case certain velocity, and in this case when it reaches that maximum point there, point P, that will simply be when your line, in this case when your graph cuts in this case the x-axis. So in this case it will simply be that point, and in this case it will in this case what would happen is that it will return to the same point, which is point C, which would be somewhere, let's say somewhere there. Let me just say it's somewhere right there. So in this case somewhere there, so that would be in this case, let's say that's T1. In this case that's let's say we have in this case T2, say that's T2 there, if T3 and T4 and so on. So in this case what would happen is that in this case this object will go down, and in this case it will in this case collides with the ground, in this case with a certain velocity. It will reach the ground in this case with in this case a certain velocity. So in this case what would happen is that, so in this case I would simply form a straight line graph again. Now this is not going to be perfect in a sense, but in this case what you must notice that after this object collides with the ground, and all of a sudden what would happen is that it would actually have a positive in this case a positive speed, and then what would happen is that all of a sudden it would actually have a positive speed in this case, and what will happen is that it will now start of course to decrease again until it reaches its next maximum point, and in this case it will start of course to fall down until of course it reaches the ground. Right now what you must notice that every time after in this case the object collides with the ground, it will lose its speed. In this case after after every bounce, in this case, its speed would be less. So in this case, now that would simply be in this case due to the fact that we know that, of course, if let's say your object reaches let's say with the reaches the ground with a, let's say, certain, let's say, kinetic energy. So what would happen is that if in this case when a ball collides with the ground, what you simply can hear in that point is that you would likely hear actually a sound, and that sound will simply be due to the lost energy. So in this case, we know that of course we can calculate in this case kinetic energy, ek, being equals to, in this case, a half multiplied by the velocity, and this will simply be multiplied by the mass, mv squared, right? So in this case, we know that of course the lesser the kinetic energy, so that would mean that the lesser, in this case, the speed. So in this case, what would happen is that in this case your object will reach the ground with a certain velocity, right, with a certain greater velocity. So in this case, after it collides with the ground, so in this case, what would happen is that this object would now leave the ground with a speed that is less than that which it arrived with. So that's one important thing that you must keep in mind. So in this case, when your object in this case leaves the ground, it would have the speed that is actually less than that which it arrived with. So in this case, that would actually happen after the collision. So in this case, we say that in this case, after, in this case, your object collides with the ground, so in this case, all of a sudden it would actually have, in this case, a positive speed, but in this case, which is less than that which it arrived with on the ground. In this case, it can to travel up, in this case, until it reaches its maximum point. So in this case again, it will after it reaches that maximum point, it will now start to fall down until again it bounces with the ground. But in this case, remember I said that after every bounce, in this case, the speed actually decreases, it becomes less and less. So in this case, after, in this case, it collides there again, its speed would all of a sudden become positive. All right, it become positive there, and in this case it will begin again to fall until, of course, it would begin to of course to go up, right? But in this case, the speed will simply be decreasing, and then until, of course, it reaches its maximum point. And in this case, it will again reach the ground and collide, and then again, all of a sudden, the speed becomes positive, and so on and so forth. So in this case, these dotted lines simply, in this case, represents the time taken over which, in this case, the object was in contact with the ground. So in this case, we simply represent it with the dot to show that, in this case, at that particular moment, we are no longer, in this case, in free fall. So in this case, there's another object that is actually, there's another force, in this case, that is actually now acting on the object. Remember that, of course, we said that vertical projectile motion, this is, of course, when we talk about vertical projectile motion, we are only considering, we say that in vertical projectile motion, there's only one force acting on the object. So in this case, when there is another force, we are no longer, in this case, in free fall. We mentioned that in this case in the first video. So in this case, what you must notice that these dotted lines that we normally have, so in this case, we normally in this case represents the time taken over which or in this case, the time taken over which the object was in contact with the ground. We normally represent it with, in this case, with the dotted line there. So in this case, that's what we normally do. So in this case, we represent it with the dotted line. So when you see that dotted line, so this simply means that in this case, this is when in this case, your object is in contact with the ground. So in this case, like I said, we normally represent it, in this case, with that dotted line. So in this case, this is what you must simply note there. Now the rest hasn't changed. We simply still note that simply know that, of course, the velocity, in this case, no man, now I'm saying something else. We know that, of course, the gradient underneath the velocity versus time graph represents the gradient, and in this case, the area underneath the velocity versus time graph still represents, in this case, the area, the displacement of the object. Now the only difference, in this case, between the tennis ball is that it bounces. In this case, the steel ball doesn't bounce. So in this case, the difference is that, in this case, your object, in this case, would have multiple maximum points there. So in this case, when your graph cuts those the y the x-axis, so in this case, when, of course, your graph in this case, when, of course, your object would be, in this case, at its maximum point. Now what you must just keep in mind is that every time in this case your object in this case collides with something, in this case it loses its speed. So in this case, after it collides with the ground, in this case the object simply loses its speed. Now after it collides with the ground, the speed to simply change direction, it will become positive, and in this case it decrease until it reaches that maximum point, and again your speed will start to increase in the opposite direction until in this case it hits the ground. In this case, when it leaves the ground, it simply have the speed which is less than that which it arrived with. So you must just keep that in mind. So in this case, scenario number 3 would be in this case. Now suppose, let's say, now all of these scenarios, scenario 1 and 2, we're projecting something. Now let's say we drop an object. Right now it doesn't really matter whether being a tennis ball or in this case a steel ball. Right, so in this case, now suppose, let's say again I was standing there, right, with an object on my hand. All right, so in this case that would simply mean that, so if I drop it, so that would simply mean that in this case the velocity of the object, the initial velocity would simply be 0. So in this case, we would know that, of course. So in this case, this is the type of graph that you're actually going to have. So in this case, we know that, of course, the velocity, when you drop something, the velocity is 0. So in this case, your graph would simply start there at the origin. So in this case, if we take upwards again as positive and downwards as negative, so in this case our graph would simply be something like that. As in this case, is when, of course, your object in this case reaches the ground there. So in this case, if it is a bouncing ball, again all of a sudden after it collides with the ground, again the velocity simply become positive, and all of a sudden there, and then in this case the speed will simply now again starts to decrease, right, until it reaches its maximum point. In this case travel downwards again, and so forth and so on. So in this case, what you simply just need to note is that when you drop an object, in this case, if you were to in this case to draw in this case the graph or the versus time graph of that object, so in this case what you simply need to know is that in this case your graph will simply starts at the origin. Now again, if we had taken upwards in this case as positive, as negative, in this case, and downwards as negatives, in this case your graph would have simply just reflected upon the x-axis. So in this case, this simply be the graph that you would have had, something like that. So in this case, all of a sudden again your velocity, in this case the speed changes direction, then you have something like that, then again all of a sudden, and so on and so forth. The same applies with this graph that we have there. Now what we're going to do, we're going to look at some quick examples, of course, of what I have prepared down there, right, which is question 1, which was actually a question which was written in June 2018. So question 1, they say that a ball is thrown vertically upwards by a boy standing on top of a building. The ball hits the ground below and bounces vertically upwards. The graph below shows the motion of the ball. Neglect any effects of air resistance. So this simply just tell us that in this case we are in free fall. This statement there, neglect any effects of air friction. So in this case, if we look at our graph, so in this case simply be in this case the starting point of the object, and then in this case when your graph cuts in this case when it cuts in this case the x-axis, so in this case simply be in this case the maximum point, and in this case it will of course return the same point of throw. So in this case what I'm going to do would be in this case just to to draw the motion of that object. So in this case we have a building somewhere there, and in this case they say that the boy projected that ball upwards. So in this case that object will go up, it will reach a maximum point there, to start to fall down, passing that point, that same point there. Now suppose let's say that's point A, that's point B, that's point C. In this case we say that of course that object will continue to go down, and in this case it collides with the ground. In this case all of a sudden, this case the speed changes direction, it reaches its maximum point, and so on and so forth. So in this case point, I'm going to represent point D as in this case the position where in this case just split seconds before in this case it collided with, in this case, with the ground. And in this case I'm going to represent that being point A, simply immediately after it in this case it collided with the ground. Then the maximum point there was simply going to represent it by F at something like that. So this simply means that in this case T1 will simply be in this case point B. This case would simply have in this case point C somewhere there, where in this case our velocity is -5. So in this case this simply be in this case on the ground at point D. Right before in this case it comes at it collides with that with the ground. So in this case this point will simply be immediately after it collides with the ground. So in this case sometimes also they represent it with a line, but in this case the most common one is where they represent it with in this case the dotted lines is seen there. Now this question, actually look at it in this case in the videos to follow. I'm trying to avoid it to make this video a 1 hour video. We don't want to fall asleep in the process of watching this, right? So in this case simply be point D, and this simply be in this case point A, and this simply be in this case point F there. So in this case for 1.1 they said that define the word projectile. I misspelled that. In this case the grammar there it just ran away, right? So in this case they said that define projectiles. In this case we know that of course projectile is when an object has been given an initial velocity and moves under the influence of gravitational force only, right? We said that so that would be the formal definition of projectile. So in this case for 1.2 they say that what does T1 indicate on the graph, or what does T1 indicated on the graph in this case represent? We know that of course T1 represent at that point. We know that this is when in this case your object is at its maximum point. So in this case T1 this case represents the maximum point. So that would be in this case T1. In this case when your graph casts the x-axis, so in this case your object to simply be in this case at its maximum point. So in this case for 1.3 they said that determine the value of T1 there. So in this case T1 would be in this case they simply want us to calculate the time taken over which, or the time taken by the object to reach its in this case maximum, to reach its maximum point. Now they didn't say whether to use in this case whether to use the equations of motions or not. So in this case what you are simply going to do would be to use those equations of motions there. So I have that formula there up there. Let me just scroll down again. So in this case remember what I said in this case what you do in this case would be to list the things that you know about those particular points. So in this case between point A and B, we know in this case the velocity initial. Now in this case if you look at this graph they actually took upwards as positive and downwards as negative. So in this case VI simply be in this case 5, as in this case we said that downwards is negative and upwards would be positive, right? So in this case our V initial simply be 5, in this case our V final simply be 0, in this case our delta T is what we are looking for. So in this case time is simply what we are looking for there. So in this case T simply be, we're going to leave that as T1, simply be in this case T1. So that's T1 there. So in this case we know that the change in displacement, so we don't know that, but in this case we know that of course the acceleration simply equals to -9.8. we chose downwards in this case as negative, right? So in this case the displacement will simply be in this case negative. Now what we are going to do would simply be to say, now again any equation, no matter that we are looking for time, so in this case any equation that we're going to choose must have time, but in this case any equation that we are going to choose must not have displacement. Why? Because in this case we do not know the displacement. So in this case what we are simply going to choose would be that first equation there. So in this case what we would simply have there would be to say Vf equals to Vi plus in this case A multiplied by delta T. So in this case what you simply have there would be V final 0, V initial that's 5, plus in this case -9.8 multiplied by delta t. So in this case, simply I'm going to take this to the other side. So it's simply be in this case 9.8 multiplied by delta t equals to 5. So in this case, if I divide by 9.8 on both sides, so in this case, what I'm going to have simply be delta t being equals to 0.51, which of course according to the scale that they have there, to simply be in this case delta t being equals to 0.5. So that would simply be your time. So that's in seconds. So that will be in this case seconds. So that's what we have there. So in this case for 1.4, they said that calculate the height of the building. Now again, they didn't specifically say whether to use, in this case, whether to use the equation of motions or not. So in this case, if they do not say, simply use, in this case, the equations of motions. So in this case, what you're simply going to do there would be to say that in this case, now the height of the building is between in this case, now what I'm going to do is simply to choose between point A and D. So that would simply mean that in this case, between point A and between point A and D. So in this case, between point A and D. So in this case, I know that in this case, V initial simply equals to 5, or V final in this case simply be, we know that in this case V final that's negative 14.6, that's negative 14.6. And that in this case, our delta t in between those 2 points, so that's simply 2 seconds. So that's 2. In this case, we know that of course delta x, we don't know. That's what we are simply trying to find. In this case, we're going to leave that as open, and in this case, we know that a would simply be in this case negative 9.8. So in this case, what we are simply going to do there would be to say that in this case, we're going now remember that of course we're looking for displacement. So any equation that we're going to choose must have displacement. So in this case, we can't choose the first one. Why? Because in this case it doesn't have displacement. But in this case, what we can do, we can choose the second one. Why? Because it has displacement, we have final velocity, and so on and so forth. And also we can also choose this one. All right, but in this case, what I'm simply going to do would be, I think I'm going to choose this one, because we already have in this case displacement being in this case isolated. So in this case, we're going to say delta x in this case is equals to, in this case, vi multiplied by delta t plus a half multiplied by acceleration multiplied by delta t squared. So in this case, I'm just going to substitute those values. So in this case, simply v initial, that's 5 multiplied by, in this case, 2 plus a half multiplied by a, which is negative 9.8, multiplied by t, which is squared, which is simply a 2 squared. So in this case, if you put that into your calculator, what you're simply going to have would simply be, in this case, your displacement being, in this case, negative 9.6. So in this case, the height of the building would simply be, in this case, the height of the building would simply be, in this case, equal to, in this case, 9.6, in this case, meters. So that will simply be what you are going to get there. So in this case, for 1.5, they say that calculate the value of T2. Now, where is T2? So in this case, this will simply be, in this case, your T2. So in this case, your T2 would be, in this case, when, in this case, your object reached that point F. Now, in this case, what I'm going to do, in this case, I know that, of course, at this point, at this point there, you know, that was after 2 seconds. So in this case, if I were to calculate the time taken by the ball to travel between point E and F, so in this case, I would know that length there. So in this case, so what I'll simply do there would be to take 2 and I add it with the value that I'm going to get there. So in this case, what I'm going to do would be to calculate the time taken over which that object, to calculate the time that object took to travel between point A and F. So if I find that time, I simply add it to 2. In this case, I'll simply get my answer there. So in this case, between point E and F, between point E and, in this case, F. So in this case, I know that, of course, V initial is equal to, so between point E and F, so in this case, V initial simply be, in this case, 10, simply be 10, positive 10. V final, that's equals to 0. In this case, we know that, of course, at the maximum point, time would simply be, in this case, 0, right? So in this case, we know that, of course, delta t, that's what you're looking for. Leave that as open. Delta x simply be, in this case, we don't know what delta x is. We don't know how far or how high above the ground that object was displaced after its first bounce. In this case, so what we're going to do would be to leave that as open. So in this case, we know that A would simply be, in this case, a negative 9.8. So in this case, what I'm going to do now, remember that I'm calculating time. So in this case, any equation that I must choose must have time, but in this case mustn't have displacement. Why? Because in this case we don't know the displacement. So in this case, what I'm going to do would be to say that I'm just going to take that first equation there. Why? Because it's easier in this case. So in this case, simply be, in this case, F equals to Vi plus, in this case, A multiplied by delta T. So in this case, Vf will simply be 0. Now I'm trying to rush because like again, I don't want to make this video the longest video alive. Right, so in this case, that's simply be, in this case, our time, our P initial will simply be, in this case, 10 plus negative 9.8 multiplied by, in this case, delta T. So in this case, I would know that I'm simply going to take this to the other side. So it's simply be 9.8 multiplied by delta T equals to 10. So in this case, divide that by by 9.8. So in this case, if I do that, you are simply going to find your T being equal to delta T being equals to, so that will simply be, in this case, 1 point, so that's 1.02 seconds. So in this case, to find, so that's seconds there. So in this case, to find that T2, so in this case, T2 would simply be equal to that time there, plus, or simply be equal to that 2 there, plus that time we found there. So in this case, simply become now 2 plus 1.02. So in this case, your time will simply be equals to 3.02 seconds. So in this case, that's simply be, in this case, your time there, seconds, right, in seconds. So in this case, if we look at 1.6, they say that use the graph, right? Do not use equations of motions to calculate the distance between the initial position of the ball and when it leaves, in this case, or when it leaves, of course, they say that calculate the distance between the initial position of the ball, which is when it leaves the boy's hand, and its maximum height after, in this case, bouncing. So in this case, what I'm going to do would be just to to redraw that graph, that thing there that I had right there. So in this case, what I would simply have would be, in this case, so I have a building right somewhere there. So in this case, my object went up, reached the maximum point, it returned. In this case, it went down, it bounced. In this case, it reached another maximum point there. So in this case, what they want is, in this case, the distance between the initial position of the object, which is the height, and in this case, they want the difference between that and its maximum point, in this case, after the first bounce. So in this case, they want that height there. I already know the height of the building to be, in this case, we say that's actually 9.6. So in this case, we know that, in this case, that's 9.6. Right, so in this case, what I can simply do would be to calculate, in this case, this height, right, which would be represented by that maximum height there after the first bounce. So in this case, after that, what I simply do would be to take, in this case, this whole length, I subtract that. In this case, I'll be left with that there. So in this case, what I'm going to do now, remember they said do not use equations of motions, right? This is weird. I don't know why they are doing that. Why? But anyway, let's do this. So in this case, we know that, of course, we know how to calculate the displacement. So in this case, we're going to calculate the displacement between these 2 points. All right, between, in this case, if we look at our graph, between, in this case, point E and F. So in this case, we notice that, of course, we can just form, let me just erase this so that we can see what's happening. Now again, let me just, so in this case, you can note that, in this case, we have a right angle triangle there. So in this case, we said that's point, so that was point, that was point E, and that was point, in this case, that was point F, not point D. So that was point F there. So in this case, our time between that would simply be between these two, between those 2 points would simply be, in this case, that 1.2 seconds there. So in this case, simply be, in this case, 1.2, that distance there. And in this case, the height would simply be that that 10 there. So in this case, from the origin until to that, so simply be, so to represent that height there. So in this case, what I'm going to do would be to say, in this case, area, area is equals to a half multiplied by, in this case, by the base and multiplied by the perpendicular height. All right, now forgive my handwriting there. So in this case, what I'm going to have would be a half multiplied by, in this case, by time. We say that's 1.02 multiplied by the height. We said that would be 10. So if we multiply that by 10, so in this case, what we are going to have, multiply by that by 10, so in this case, what you're going to have, you put that into your calculator, would simply be, in this case, 5.1. So in this case, what you would now do there would be to say, so in this case, we say that in this case, to calculate the difference between, you simply take that 9 and you subtract that, in this case, the maximum height of that object after the first bounce. In this case, would simply get the difference there. So in this case, what you're going to say would be to say, in this case, the distance between, I'm just going to leave it as between, this is between these 2 points, will simply be equal to, in this case, to 9.6. In this case, minus that 5.1. So in this case, simply be equals to 4.5 meters. So in this case, that would be, in this case, how we would tackle that question. So in this case, the rest of the questions, I'm just gonna look at it in the following video. Unfortunately, I'm avoiding to make a longest video alive, which is what I'm trying to avoid. Yeah, although it is already the longest video alive, but otherwise, ladies and gentlemen, this is the end of this video. Now, if of course this video helped you at some extent, be sure to leave a thumbs up. Right, of course, if you haven't subscribed, be sure to subscribe and become the part of the family. And also, of course, I'm just gonna do this question in the following video right now. You can attempt it if you want, and in this case, you can just simply look at the solutions when I do it in the next video. But otherwise, ladies and gentlemen, as the story always ends, this is Mike signing out. Sharp sharp.